Welcome to the Static Routes module. By the end of this module, you should be able to configure and monitor static routes. Static routes are routes that are manually configured. They are often used to provide a default route to the Internet from within a network, or to provide a route to a customer or partner network. All configuration for static routes occurs at the Edit Routing Options level of the hierarchy. Static routes must have a valid next hop defined. Often the next hop value is the IP address of the neighboring router headed towards the ultimate destination. On point-to-point interfaces, you can specify the egress interface name as the next hop rather than the IP address of the remote device. Another possibility is that the next hop value is the bit bucket. This phrase is analogous to dropping the packet off the network. Within Junos OS, the dropping of packets is represented with the keywords reject or discard. Both options drop the packet from the network. The difference between them is in the action the device running Junos OS takes after the drop action. If you specify reject as the next hop value, the system sends an Internet Control Message Protocol or ICMP network unreachable message back to the source of the IP packet. If you specify discard as the next hop value, the system does not send back an ICMP message. The system drops the packet silently. By default, the next hop IP address of static routes configured in Junos OS must be reachable using a direct route. Unlike routing software from other vendors, Junos OS does not perform recursive lookups of next hops by default. Static routes remain in the routing table, also known as Routing Information Base, or RIB, until you remove them or until they become inactive. One possible scenario in which a static route becomes inactive is when the IP address used as the next hop becomes unreachable. The basic configuration syntax for IPv4 and IPv6 static routes is displayed. The No Re-Advertise option, which prohibits the redistribution of the associated route through the routing policy into a dynamic routing protocol, such as OSPF. It is recommended that you use the No Re-Advertise option on static routes that direct traffic out the management Ethernet interface and through the management network. Note that IPv6 support varies between Junos devices. Be sure to check the technical documentation for your specific product for support information. The displayed example shows the basic verification steps when determining the proper operation of static routing. You can use Show Route Protocol Static to display static routes and the Ping utility to verify end-to-end reachability. By default, Junos OS requires that the next hop IP address of static routes be reachable using a direct route. Unlike software from other vendors, Junos OS does not perform recursive lookups of next hops by default. As illustrated, you can alter the default next hop resolution behavior using the Resolve CLI option. In addition to the Resolve CLI option, a route to the indirect next hop is also required. Indirect next hops can be resolved through another static route or through a dynamic routing protocol. It is recommended to use a dynamic routing protocol as the method of resolution whenever possible. Using a dynamic routing protocol rather than a static route to resolve indirect next hops dynamically removes the static route if the indirect next hop becomes unavailable. The qualified next hop option enables independent preferences for static routes to the same destination. In the sample configuration shown, the 172.30.25.1 next hop assumes the default static route preference of 5, whereas the qualified 172.30.25.5 next hop uses the defined route preference of 7. All traffic using this static route uses the 172.30.25.1 next hop unless it becomes unavailable. If the 172.30.25.1 next hop becomes unavailable, the device uses the 172.30.25.5 next hop. Some vendors refer to this implementation as a floating static route. Welcome to the Dynamic Routing module. By the end of this module, you should be able to describe the functionality of dynamic routing. Static routing is ideal in small networks, where only a few routes exist, or in networks where absolute control of routing is necessary. However, static routing has certain drawbacks that might make it cumbersome and hard to manage in large environments, where growth and change are constant. For large networks or networks that change regularly, dynamic routing might be the best option. With dynamic routing, you configure the network interfaces to participate in a routing protocol. Devices running routing protocols can dynamically learn routing information from each other. When a device adds or removes routing information for a participating device, all other devices automatically update. Dynamic routing resolves many of the limitations and drawbacks of static routing. Some of the general benefits of dynamic routing include lower administrative overhead. The device learns routing information automatically, which eliminates the need for manual route definition. Increased network availability. During failure situations, dynamic routing can reroute traffic around the failure automatically, as the ability to react to failures when they occur can provide increased network uptime. Greater network scalability. The device efficiently manages network growth by dynamically learning routes and calculating the best paths through a network. To summarize the key points related to dynamic routing protocols, interior gateway protocols, or IGPs, operate within a single autonomous system. The single network administration provides unique routing policy and flexible use of network resources. Examples of IGPs include RIP, ISIS, and OSPF. Exterior gateway protocols, or EGPs, operate among different autonomous systems. In general, EGPs are used by independent administrative entities to communicate between independent network infrastructures. The current EGP that is used is BGP. Welcome to the Configuring OSPF module. By the end of this module, you should be able to configure and monitor OSPF. OSPF is a link state routing protocol designed for use within an autonomous system, or AS. An AS is a set of routing devices that are managed by a single organization or corporation. OSPF is an interior gateway protocol, or IGP. IGPs are designed to facilitate communication of routes between routers within the same AS. Link state protocols enable for faster reconvergence, support larger internetworks, and are less susceptible to insufficient routing information than distance vector protocols, such as RIP. Devices running OSPF send out information about their network links and the state of those links to other routers in the AS. This information transmits reliably to all other routers in the AS by means of link state advertisements, or LSAs. The other routers receive this information, and each router stores it locally. This total set of information now contains all possible links in the network. In addition to flooding LSAs and discovering neighbors, a third major task of the link state routing protocol is establishing the link state database, or LSDB. The link state or topological database stores the LSAs as a series of records. The important information for the shortest path determination process is the advertising router's ID, its attached networks and neighboring routers, and the cost associated with those networks or neighbors. OSPF uses the shortest path first, or SPF algorithm, also called the Dijkstra algorithm, to calculate the shortest paths to all destinations. It performs this calculation by calculating a tree of shortest paths incrementally and picking the best candidate from that tree. OSPF uses areas to enable for a hierarchical organization and to facilitate scalability. An OSPF area is a logical group of routers. The software can summarize the routing information from an OSPF area, and the device can pass it to the rest of the network. Areas can reduce the size of the LSDB on an individual router. Each OSPF router maintains a separate LSDB for each area to which it is connected. The LSDB for a given area is identical for all participating routers within that area. To ensure correct routing knowledge and connectivity, OSPF maintains a special area called the backbone area. OSPF designates the backbone area as Area 0. All other OSPF areas must connect to the backbone. All data traffic between OSPF areas must transit the backbone. This is a use case to understand how OSPF works. The displayed topology is used in this use case. The objective of the use case is to use a single OSPF area to provide connectivity among all connected subnets and loopback addresses, and to ensure that no adjacencies are formed on interfaces connecting to the 172.20.x.0/24 subnets. The OSPF configuration required for router A is displayed. Although not shown, router B and router C require a similar OSPF configuration to establish adjacencies and share routing information. You use the Show OSPF Neighbor command to determine OSPF adjacencies. You can also use the Detail or Extensive options for added information. In the sample output displayed, you can view that router A has formed adjacencies with both router B and router C. The following list is a description of the fields displayed in the output. Address, the address of the neighbor. Interface, the interface through which the neighbor is reachable. State, the state of the neighbor, which can be a temp, down, exchange, xstart, full, init, loading, or two-way. Here, the state of the adjacencies shows full, which means neighbors can exchange routing information. ID, the router ID of the neighbor. Pri, the priority of the neighbor to become the designated router, used only on broadcast networks during designated router elections. By default, this value is set to 128. The router with the highest priority most likely to be elected as the designated router. Dead, the number of seconds until the neighbor becomes unreachable. The sample code displayed illustrates the Show Route Protocol OSPF command, which displays the OSPF routes learned by router A. Note that router A does not install its directly connected subnets in its route table as OSPF routes. It installs them as direct routes. Welcome to the Routing Using IPv6 module. By the end of this module, you should be able to describe how routing works using IPv6. IPv6 is already enabled on Juniper routers, so no global command is required. You must, however, configure IPv6 packet processing on an interface by adding family INET 6. Enabling IPv6 on an interface automatically configures the interface's link local address and activates IPv6 processing for that interface. Additional addresses can be configured, and the link local address can be manually configured to override the automatically created address. As you can view from the displayed example, explicitly configuring an IPv6 address on an interface differs from configuring an IPv4 address only in that you use family INET 6 and an IPv6 format address. For multi-access networks, /64 prefix lengths are most commonly used. For point-to-point links, many prefix lengths have been used, including /64, /124, and /126. But the current best practice according to RFC 6164 is to use the /127 prefix length. Simply entering the configuration command set family INET 6 will cause IPv6 packet processing to be enabled on the interface and a link local address to be generated. If you configure EUI64 addressing, the router automatically generates an interface ID based on the interface's MAC address. Refer to RFC 4921 and its updates for further information. IPv6 static routes are conceptually identical to IPv4 static routes. Configuration in Junos is also similar for IPv4 and IPv6. As with IPv4, IPv6 static routes are configured at the Edit Routing Options hierarchy level. The only difference is that for IPv6, you need to specify the IPv6 routing information base, or RIB, also known as routing table, which by default is INET 6.0. As shown in the example, a link local address may be used as the next hop for an IPv6 static route, but the outgoing interface must also be specified, since link local addresses are not globally unique. OSPF version 3, or just OSPF for IPv6, is defined in RFC 5340, with some additional features, such as graceful restart and authentication, defined on separate documents. RFC 5781 defines OSPF v3 graceful restart, and RFC 4552 defines authentication, confidentiality for OSPF v3. OSPF v3 maintains the fundamental mechanisms of OSPF, including link state advertisement or LSA flooding scopes, areas, designated router election, stub areas, not so stubby areas or NSSAs, and so on. However, some changes are necessary to account for the differences in IPv4 versus IPv6 addressing. Notwithstanding the differences under the covers, for you to configure OSPF v3 on Junos OS, all you need to do is replace OSPF with OSPF 3 in your configuration commands. You enable OSPF v3 almost the same way you enable OSPF v2. The only difference is that you use the OSPF 3 statement in place of OSPF at the Edit Protocols hierarchy level. All OSPF v3 operational commands include the identifier OSPF 3 in place of the OSPF option.